Okay.
Hello. Hi. Can you hear me?
Yes.
Yeah.
Very good. Yeah, I'm sorry I'm so late. I just had to update my Zoom as usual.
Okay. Andrew, am I pronounced right?
Yes, very good.
So you will be the first speaker on the would you like to try to share your screen?
Yeah, I will try to do that. Just 1 second. So here we go. Sorry. Okay. So let's try. Can you see my screen?
Yes.
Aha.
Could you first greet it?
Sorry? Full screen. Yeah, sure.
Yes.
Wait a sec. That's the wrong one. This one.
Okay, that's good.
Perfect.
Okay.
So just let me know when I should start.
Yeah. We will start our seminar. Okay. Again, 2 p.m. CEST. Welcome to NLA today. Marcel will manage questions on Zoom. Hi, Marcel. I'm sorry. Yeah. And Davide will on YouTube.
Hi, everyone.
Okay. Today, our first speaker is Andrew Gore. He is CEO of EMS Press. Today, he will give us on the topic of startup and publication house. So, Andrew, please take over.
Yeah, thank you very much. So I'm very happy to speak here today. So I want to give a brief overview about what I have been up to during the last years. So it's always a bit weird to just talk about myself. So in case you have any questions, feel free to just ask them right away, or we also have this discussion session afterwards, I think. So there will be some time for that also later. So I want to start with the overview of this talk. So am I correct that I have like 20 minutes for this?
Yes.
Very good. Okay, so let's get started. So I want to first talk a bit about my mathematics background, or what I've been studying, my PhD, and some software I'm developing. Then I want to talk about my startup Paperhive briefly, some bits about my role in blockchain research and consulting. That's maybe a shorter one, but nonetheless maybe interesting for some. And then what I'm currently mostly doing is EMS Press, which is a publisher, and I want to talk a bit about sustainable open access publishing. So let's get started with my mathematics background. So I studied mathematics in Bonn in Germany and in Erlangen, with computer science as my minor subject, and I was pretty much always quite in love with numerical analysis and numerical linear algebra. So that's my home turf, mathematically speaking. And my diploma thesis was on domain decomposition methods for finite elements in an image segmentation and detection setting. And after this, I went to Berlin and did my PhD here at the Technical University. That's actually where I'm currently based. So I'm actually in my office at the university, and no one else is at the university here. My supervisor was Jörg Liesen, and the whole PhD and the project was part of the Matheon Research Center. My PhD thesis was about, or still is about, recycling Krylov subspace methods for sequences of linear systems. And the general question was, so let's assume that we have solved some linear system, A1, X1 equals B1, with some Krylov subspace method, for example, GMRes, MinRes, or CG. That will produce some data, let's call it D1. And so I don't only mean the solution, the approximate solution, let's say X1 tilde or something, but I also mean all the data that is produced during the inside the algorithm, Ritz values, Ritz vectors, so the basis of the Krylov subspace, and the matrices that are involved. If we have solved this for one linear system, then if we have a similar linear system in the sense that the matrices or the operators are similar, how can we recycle data from this first solution process to solve the second and subsequent linear systems more efficiently? So that was the general question. There have been several approaches to this based on augmentation techniques and deflation techniques. And so the answer is you can just use projections in there to get rid of parts of the, let's say, for example, of the spectrum, or like hide certain subspaces from the Krylov subspace method that make it, let's say, difficult to come to a solution quickly. In the thesis, I was mostly picking the recycling vectors based on a priori bounds or approximate Krylov subspaces. So you have already data, which is cool. Like you solved one system and you have data, and then you know something about the changes to the next system. And then you want to reuse data, and you can then perturb the original system bit and see how a different linear system would perform with the same solver. So that's what I did in my PhD. I was writing some software along with this. I'm a big fan of free and open source software. And also open access of data and publications. So my PhD thesis is available, including all sources and like the LaTeX sources, but also the code sources on GitHub. And I developed a software package that is still used for Krylov subspace research. So you can basically run a Krylov subspace solver and look into every single part of it and make adjustments if you want to study those methods a bit further. So that was my mathematics background, and I'm coming to the Paperhive phase, which is a very interesting project that I started more than 6 years ago now. Directly after my PhD, I was quite frustrated with the status quo of publishing, where the discussion of articles happens in very long cycles. Let's say, for example, seminars or emails, or this never happened. one question that I usually had when I was reading a paper at some point in the text was, what did other readers of this article think when they stumbled over, let's say, this formula here or this formulation? That was one question that I always had. And then I said, look, let's build a platform where you can collaborate with discussions in articles while you read them. That was the idea of Paperhive, and it still is. So on Paperhive, you can discuss articles in public discussions or also in private channels. And some people use it for research, some people use it for peer review, some for research group discussions. And I really wanted to bring this GitHub style collaboration to academia or academic publishing. So since I'm dealing a lot with open source software, I was thinking this process that you have on open source software, where you really change things quickly and work together and discuss code, why can't we have the same for academic papers? And I just want to share one screenshot. I hope this is a bit visible here. This is how Paperhive looks like. So you have the document in the middle, some metadata on the left, and on the right is the discussion column, the margin where you can freely type and add comments to specific parts in the text and then have a discussion on them. So this includes some minor things like typos, but also like other proof ideas, or any meaningful addition to a paper. Questions, references, code, whatever you want. So this platform is live. I wanted to briefly tell you a bit about the journey, how we got there. Since I think that might be interesting for others as well to maybe participate in a startup or found a startup even. At the end of 2014, this idea came up with a coworker from the university here. We first checked some funding options and then realized we really need to build a prototype. Otherwise, you're talking about hot air. And it's really difficult to sell something to people, not in the sense of really earning money, but to convince people about something if you only have a plan. So if you have a prototype, that is a lot easier. And we started building this in the basement of a hacker space here in Berlin. And in 2015, with this prototype, we were accepted at the TU Berlin Startup Accelerator. And applied for funding. There is a funding program here in Germany, and I think it also exists in other European countries, possibly on a different name. It's called Exist here, which gives you, if you can manage to get it, they accredit you around 130,000 euro for a year to build your business and support 3 people with this. We were looking for another co-founder during that time and found him. So that was very helpful to have also a business person on board. And in 2016, we went live with 2 million articles from archive.org. That was the start. Then we changed our business model. This also happens very frequently with startups. You realize that the original one doesn't work. Or was not very, let's say, well tuned to your customers, and we switched to publishers. So publishers should be the ones who pay for the service and not researchers. We had also, like every startup, a big crisis with a co-founder. Huge trouble. Eventually it worked out well and we found a replacement, but it was quite stressful. In 2017 we had the first contracts with publishers, smaller ones, Transcript, Language Science Press, but also pilots with bigger ones like Springer Nature. And in 2018 more research groups and students started using the platform. And so the platform is running. So that's the journey. I could tell you a lot more about it, but maybe not on this slide, perhaps in the discussions if you're interested. The thing is, the platform is live and well. I plan to do a relaunch with some technology upgrades, but you can check it out on Paperhive.org and see how it works. Then I did something completely different, which is I was moving a bit into this blockchain space. I always found this quite interesting, blockchains as such. So I was talking to the founder of a Berlin-based startup called Satoshi Pay, and they needed a replacement for Bitcoin, but they needed a mathematician to understand these white papers. That's how they call them in the blockchain space. So unreviewed articles. I wouldn't even call them preprints. It's quite early phase material, and that's what they build their blockchains on. So it's really a bit weird, and millions or billions of dollars or euros go into these systems where people have never really spent enough time to figure out the mathematics behind it. So this blockchains, I find this really interesting. Because they consist of one part which is called the consensus algorithm. So how do these distributed nodes in a blockchain network reach one common agreement? So how do they find consensus? And then there is some cryptography bit involved, which is mostly standard asymmetric cryptography, like public and private key based, and that's for me not too interesting. I was more interested in the consensus algorithm, but the cryptography also has some really interesting developments there, like zero knowledge proofs and things like that. So I was getting into that as a side project. Cryptocurrencies, which are basically blockchains plus some buzzwords or some minor technical layer, are more or less boring for me. It's that's a lot of hype, and I was more interested in the technology and the mathematics behind it. So I was investigating new blockchain types, like based on directed acyclic graphs, DAG based, or there's a comma, or federated Byzantine agreement systems, which work fundamentally different from Bitcoin, which consumes a lot of energy, and we don't. I hope we agree that we don't want this energy consumption. Then I started also a research project besides consulting this company. So researching these federated Byzantine agreement systems, which was also funded by the Stellar Development Foundation. So yeah, wrote 2 papers about that. You can check this out. I shouldn't go into details here because time is running. But the idea is to analyze the blockchains mathematically and see how decentralized are they really. Then my current big project is EMS Press. So I started in 2019 as the managing director of EMS Press, which is the publishing house of the European Mathematical Society. And we are publishing 21 books and 21 journals and around 200 books. And the EMS wanted some change. That's why they came to me. I've never run a publisher before that, so this was also a change for me. But through Paperhive, I had a lot of insights into the publishing industry and figured out ways how to improve things. The publishing industry is very slow, and the EMS wanted something modern in several ways. So they wanted, first of all, a fair and sustainable open access publishing model. And they wanted state-of-the-art publishing technology, which from Paperhive I could easily bring to a publisher as well. And then they wanted to move the publishing house from Switzerland to Germany for administrative reasons. So having a base in the EU. So this was very interesting in the beginning. I first declined and said, no, I'm not doing this. But then they said, I can really completely renovate this publishing house and make everything different. And that was interesting to me because I have several points with the publishing industry that should be done in a better way. And the first is the business model. So what's the problem currently? We have paywalls for reading, so articles can only be accessed with subscriptions, which are very expensive often. This excludes readers. But I don't need to tell you how to get articles, so you usually find some way to get them, ask a colleague or go here, go there. The better solution would be if the articles would be open access in the first place. And that's what publishers did. How they did it was catastrophic. They introduced another paywall, but this time for publishing. So commercial publishers basically charge authors article fees. Often in the range of 2,500 euro per article. That's what you have to pay as an author for making an article open access. We think, as the European Mathematical Society, that this is completely against all scientific progress. You deny authors the right to publish, which has also implications on their careers. So imagine if you're applying for a professorship somewhere and you can't even publish. So that's a problem. Publishers are pressured to sacrifice quality. If every article that has attached 2,500 euros, then it's quite natural that the publisher says, why can't we just accept more papers? So this is a trap. Also, libraries are excluded from the process. They did something in this whole ecosystem. They provided quality assurance. They picked the right journals that people need. This is also gone. And it's extra work for authors. So you need to deal with billing suddenly, but you should be doing research instead. So what's the solution? I'll skip this. Those are the requirements. The solutions that we are using now is called Subscribe to Open. Which is where libraries just continue subscribing to the content they need. So everything as before, with only one small difference. If a journal receives enough subscriptions for a certain subscription year, and enough means it reaches its sustainability threshold, so covers its costs, then this journal is published open access during this year. If not, then only subscribers have access. So as before, benefits, of course, no author fees, no extra work for anyone, open access for all if the publishers and the libraries operate sustainably. And that's what that's where we are now. We want libraries and also researchers to understand why this model is really superior to any fee-based model for authors. And this includes like the big deals that we've seen in the recent years where countries pay an enormous amount of money to commercial publishers just for these article fees. It's not taking into account anything that is happening outside the country where such an agreement is happening. So you're excluding people, and that's not what we want. So I'm coming to the end now. I noticed my time is running out. The current state is that we are now, we started offering this subscribe to open for the 2021 subscriptions. So for this year, we started with this in the last year, and the result of this first round is that all of these 10 journals that we put into this subscribe to open experiment are published as open access now. So it's working. And among these journals is also our flagship journal, GEMS, the Journal of the European Mathematical Society. So you can read all those 10 journals for free on the EMS Press site for this year. And of course, everything that has been open access once remains open access. There are several more journals to come for this S2O, and we hope to publish everything on Subscribe to Open for the next year already. Yeah, we also had the Institute of Henri Poincaré approach us about the journal C, Analyse non linéaire, which is now moving to EMS Press from Elsevier. And one key reason was also the sustainable open access publishing that we're doing, which Elsevier cannot guarantee to them. That's it. I'm happy to discuss further with you. I hope that was interesting. There are several paths there in what I've been doing, and I'm happy to talk about anything there. I just hope it was interesting for you. Thank you.
Thank you. Marcel, is there any questions on Zoom?
Yes, we have a question by Jemima, and she asks, do you think this publishing approach will be attractive to commercial publishers or only for society presses?
That's an excellent question. And ideally, this would be attractive to all publishers. But I think it's the natural publishing model for society presses because they have an incentive to serve their communities. That's their purpose. So while commercial publishers, by definition, have a primary goal of making as much money as possible. And this is easier with per article charges or fees. Right, so if you can just get 2,500 euro per article, you just need to increase the amount of articles that you publish and you have more money. So that's a very natural dynamic. I'm not saying that all commercial publishers are misbehaving on the scientific side, not at all. But the incentive is there, and we have heard about editorial boards that have been approached by the publishers to accept more articles, which is scientific misconduct, I would say. Yeah. So I think some commercial publishers are also thinking about adopting the model. So we have De Gruyter with one journal on Subscribe to Open, and there are several other publishers who are interested in this model. Like Sage, for example, but currently it's mostly the society presses who are into Subscribe to Open, really.
Okay, thank you. Davide, is there any questions on YouTube?
No, we don't have any questions on YouTube, but I actually have a question, if I may. And it's actually on the same line of Jemima's question. So many publishers are private, and in your framework, they're supposed to declare that they got enough money for that year, and then, yeah, let's go open access for this year. But this, I mean, we should rely on their honesty, or you envision like a kind of like an entity that is supposed to check that this happens, or what?
Yeah, that's a very good question. So for us, it's the European Mathematical Society who checks up on us. So we have so we are the publishing house. We're a bit a separate entity from the society, but the society is checking up on us, right? So they want, of course, the best for the community, and we want that as well. So for us, there's no real issue. Still, we want to be more transparent in this, and make public certain figures of this process. Also, the way how we decide whether a journal is sustainable and will become open access or not. So this process is basically a formula. You plug in all the data that we have as a publisher, revenue, submissions, and so on, and then it will spit out what the status of the journal is. And there is some solidarity between the journals. So sometimes a journal is performing less well in a certain year, but that shouldn't mean that it should go directly behind a paywall or anything. So we have some balancing or smoothing between those journals. And yes, I think there should be more transparency in this whole process, both like how it's done, but also feeding back more data to the community. So we are happy to publish what it actually costs to produce these articles. And I can tell you it's not 2,500 euro. It's a bit less than half. So you can imagine what profit margin these publishers have.
Sure. Thank you.
Welcome.
Okay, thank you again for Andrew's wonderful speech. Okay, Andrew, could you stop your screen?
Yeah.
Yes, thank you. Okay, our next speaker is Spyros Pokakioters. Spyros is a PhD student at University of Edinburgh. He is working on optimization and numerical linear algebra. Today, the title of his presentation is Preconditioning for an Interior Point Method of Multipliers. Spyros, please go ahead.
Thank you very much for the introduction, and as well as for having me here. I'm very glad to give a talk. So today I'm gonna be talking about a method which, as you said, we call an interior point proximal method of multipliers, and specifically about its application to convex programming. This is a joint work with my supervisor, Jacek Koncio, as well as Luca Perkamalski and Heles Martinez and John Pearson. Okay, so initially, I want to talk about the model on which I'm going to be focusing. And in particular, I'm going to be focusing on primal dual pairs of convex quadratic programming. So this is the primal in the standard form, and it's dual. And for these sorts of problems, we know that feasibility is implied if there exists a triple satisfying the KKT conditions. And I want to also notice that a QP solver can serve as a basis for general nonlinear convex solvers. In light of that, I want to focus on convex QPs, mentioning here and there possibilities of extending to convex programming. Okay, so the method, in order to derive it, I'm going to follow the standard augmented Lagrangian approach, and I will be calling it from now on as IPPMM. Okay. So the way augmented Lagrangians work is that at every iteration k, we choose some primal and dual estimates. Here we call them zeta and eta respectively, as well as some penalty parameters. So we have the barrier parameter mu, the primal penalty rho, and the dual penalty delta. Now, using all the previous, we can form a mixed barrier augmented Lagrangian penalty function. And if you ignore the last term, this is nothing more than the augmented Lagrangian. So we simply append to it some logarithmic barriers. So the way a standard augmented Lagrangian would work would be to update x by minimize x in the penalty function, and then update the dual variables using dual ascent. However, if we take these two steps and merge them, we can write them equivalently as a nonlinear system of equations. And now we can focus on solving this approximately using a neighborhood scheme. In particular, what I mean by that is that we apply a variation of Newton's method. Here in the left-hand side, we have the Jacobian, but we perturb the right-hand side using a centering parameter sigma. So sigma multiplies all the penalty parameters. And in essence, what it does is that it determines how fast these parameters are going to decrease in the next iteration. Now, the reason I call this a neighborhood scheme is that after computing the direction, we have to find a step length so that the new iterate belongs to an appropriate neighborhood. Now, concerning the barrier parameter, we update it as is usually done in zero-point methods. And most importantly, the penalty parameters are set so that they are of the same order of magnitude as mu, as the barrier parameter. Finally, to conclude the algorithm, the estimates are only updated if we have certain conditions holding. In particular, we update them if we have contraction in both the primal and dual infeasibilities. Okay, so briefly mentioning some theoretical results. If we assume that the problem under consideration is actually feasible, means that it admits a bounded solution, we can prove that the algorithm is going to converge to an epsilon optimal solution in a polynomial number of steps. And to our knowledge, this is the first polynomial complexity result for regularized IPMs. And this is important because on the one hand, you get the good convergence behavior of IPMs. And on the other hand, we get the numerical stability from the regularization, which will become apparent later. And the previous result can be generalized or has been generalized for linear semi-definite programming problems. And it holds even if the Newton system is actually solved inexactly. Now, what this means is that we can get a polynomial convergence algorithm for second-order conic quadratic programming problems. And importantly, we can exploit iterative linear algebra. And this is going to be the focus of this talk here. Before that, I should mention what happens when infeasible problems are tackled. So here we have two premises. The first premise says that these two sequences will remain bounded. The second premise says that there does not exist a triple satisfying the KKT conditions. Now notice for convex QPs, this is equivalent to infeasibility. So the theorem says that given infeasibility, the first premise cannot hold. What this means is that either of these two sequences is going to grow unbounded, and this is a necessary condition for infeasibility. On the other hand, I said that the estimates are updated if we have contraction in the primal and dual residuals. So naturally, because of infeasibility, this will stop happening after some point. So combining these two facts, we can actually design a very cheap and very quick to implement infeasibility detection mechanism. Okay, so now focusing on iterative linear algebra, I should note that for IPPMM, as well as for any other interior point method, the main computational bottleneck is solving the Newton system. And usually, if our objective is actually separable, we want to pivot certain variables to get a positive definite system, which we call the normal equations. So here's the normal equations matrix for our case. And the first thing we do is we approximate Q, the Hessian, by Q tilde, which is its diagonal. Now we want to find a preconditioner for the approximated normal equations matrix, which we call M tilde. And in order to understand how this is done, we have to understand how the IPM scaling matrix works. So theta here is a diagonal matrix that has some very large and some very small elements as IPM closes in optimality. What this means is that this is the source of the inherent ill conditioning within IPMs, but it also gives us information on which variables of the problem are actually not so important. Given this, we actually approximate M tilde by this precondition, which we call P and E. And the only thing we do is that we replace G inverse by a diagonal matrix E. Now, the diagonal elements of E are set to 0 if the respective diagonal element in G inverse is smaller than some constant times the barrier parameter, and otherwise it takes this value. So essentially, when we do that, what happens is that by setting an element to 0, we're taking the respective column of A and we're throwing it away. So we're sparsifying the normal equations. And of course, how good this preconditioner is should depend on how we choose this constant. Okay. So some basic spectral analysis shows that the eigenvalues of the preconditioned system will be greater than or equal to 1 and smaller than 1 plus a constant. Now, to see how this constant behaves, firstly, we will notice that the quotient mu over delta is order 1. And the reason for that is algorithmic. I said before that we tune the penalty parameters, the regularization parameters, to be of the same order of magnitude as the barrier. Hence, if this maximum singular value of A as well as C are reasonable, we have a well-conditioned matrix. Now, on the other hand, C is actually what determines how good the preconditioner is. In particular, if it is very large, the preconditioner is very cheap to compute, but it yields some very large outliers. If it's small, it needs a lot of memory. So we're using some a posteriori measures to tune this while the method is running dynamically. Now, for separable convex programming, where m tilde is actually equivalent to m, because we have a diagonal Hessian, you can use this directly as a preconditioner within PCG. And for non-separable programming, we actually utilize this preconditioner. I'm going to discuss this later. Before that, however, I want to mention what happens if we have certain outliers that are hindering convergence and how we can fix this. In particular, when we detect this behavior, we can choose to fix these outliers by means of BFGS low rank updates. So this is the tuning of the preconditioner. And all that this does is that it takes the p largest eigenvalues of the preconditioned matrix and sets them to the value mu. And you can show that in exact arithmetic, this does not perturb the remaining eigenvalues. Of course, we don't do this in exact arithmetic, but as you will see in practice, it's not a big problem. Okay, so in the case where we have non-separable Hessian, non-separable objective function, we have to resolve into solving the augmented system. And essentially, what we prefer to use symmetric solvers, and specifically MinRes, over non-symmetric solvers like GMRes, because the latter are way more difficult to actually predict and control. So MinRes has a coefficient matrix like MAS here, which is a saddle point matrix, a regularized one. And we need a positive definite preconditioner. And for that, we choose a block diagonal approximation where the 1-1 block here is an approximation of the 1-1 block of M, where Q has been substituted by its diagonal. And the Sur complement is approximated by the preconditioner I discussed earlier. Now, given this setup, we can define these two matrices. So M hat here is exactly the matrix we analyzed earlier in the previous theorem. And F hat is the approximation of the 1-1 block. And given the bounds on these matrices, you can prove that the eigenvalues of the preconditioned system will lie in one of these two intervals. Now, the important thing is that usually the issues arise from the approximation of the Sur complement and the maximum singular value of beta and E. And as you can see, this appears with a square root here. So we expect rather good conditioning. And because we're using MinRes, eigenvalues are the primary thing that concern us. Okay. So far I've been talking about general purpose preconditioners. However, it might be the case that you have an application that has specific structure and you would like to solve it very efficiently. And you can actually do this quite easily with a solver like IPPMM by means of changing the precondition. So when you want to tailor your solver to a specific application, the only thing you have to do is to tailor your preconditioner. And we actually did this very successfully for various sparse approximation problems. So we solved portfolio selection, classification of MRI data, TV-based Poisson image restoration, and regularized logistic regression. And you can notice that the last two problems are inherently nonlinear convex. And the extension of the algorithm to this case was actually quite easy. And in every one of these examples, we had a method that was competitive with state-of-the-art first-order approaches that are traditionally used for these problems because of their sheer size and complexity. So this goes to show that first, you can very easily write an application-specific IPPMM solver, while on the other hand, it can be very competitive with first-order approaches. Okay, so now some numerical results. I should mention that everything that I will run here I will show here is run in a personal computer. We do not allow IPMM to run for more than 200 iterations, 100 iterations for PCG and 300 for MinRes, and the tolerance is 4 digits. Okay. So initially, some computations on standard test sets show how reliable the method is. In particular, we ran 96 problems from the netlib collection, as well as 127 problems from the Maros-Mezaros convex QP collection. And we request for decreasing tolerance. And as you can see, first of all, the method is extremely robust. It solves a good chunk of the problems. And this happens even as we decrease the tolerance. And also you can see that the increase in CPU time as well as iterations is very reasonable as we decrease the tolerance. On the other hand, we can test the infeasibility detection mechanism by running the 28 problems from the netlib infeasible test set. And we observed that we have a detection success rate of 78%. And I should mention that this is a rather pessimistic way because we didn't have any false positives in the feasible libraries, which is very important. And also we should note that this detection mechanism comes also almost for free from the method. Okay, now I want to stress the effect of the low rank updates. And to that, I have to introduce some notation. So here LR, P, and tol means that we approximate P eigenpairs with tol as tolerance. And the value of the outliers is set to nu equals 10. Also, I should mention that in IPPMM and in IPMs in general, we rarely solve a single system. We usually solve a predictor and a corrector. And here you can see how PCG converged for problem NAC20 in iteration 12 with a standard preconditioner and then with preconditioner with certain low rank tunings. And in particular, the sweet spot is achieved by tuning 10 eigenvectors. And as you can see, there's a decrease in Krylov iterations, and as a consequence, a decrease in total CPU time by 15% over the non-tuned one. And the same can be seen here from convergence profiles, where we have the PCG iterations and the linear residual norm. Both the predictor and the corrector converge much faster for the tuned preconditioner. Okay, finally, to stress the importance of iterative linear algebra, I ran the method against an equivalent method that uses factorization, which can be found here, over 30 large-scale linear programming problems. And as you can see, the method, the inexact method, is actually much more efficient as well as robust. So efficiency is measured in performance profiles by how fast a line goes up, while robustness is measured by the maximum achievable percentage. And as you can see, 20% of these problems were not solved by the factorization approach because of memory issues. On the other hand, the overhead we have by inexactness in terms of number of IPM iterations is actually quite reasonable. Okay, and to wrap this up, at the moment, we're actually developing some extensions to the linear algebra phase. In particular, we're extending the preconditioner to be able to deal with dense rows or columns of A, as well as providing some equivalent alternatives. We have been re-implementing the public solver, which is right now almost twice as fast. And we're starting some new preconditioners for the non-separable case. Finally, and this is a long shot, we're trying some matrix-free implementations, but I'm not sure how this is going to go. So here are some of the references I showed earlier, and thank you very much for your attention. Let me know if you have any questions.
Thank you. Thank you for your wonderful talk, Boris. Marcel, is there any questions on Zoom?
Yes, we have two questions by Margherita Porcelli, and she asks, so first of all, she says, thank you very much for the very interesting talk. You discussed IPPMM for quadratic programming, but you mentioned that you also worked on semi-definite programming problems. Have you analyzed preconditioning for the SDP case too? Do you think that it could be somehow generalized to the SDP case, and do you see any critical issue? And then she also asks how you compute the proximal step in your applications.
Okay, great, thanks. So for the first question, I actually haven't implemented a solver for the case of SDP. And it was mostly a theoretical result to see how far we can go with a polynomially convergent regularized IPM. So to be honest with you, I'm not sure how to precondition effectively in the case of SDP, because but my first guess would be to find preconditioners and actually find symmetrizations that allow you to solve the augmented system in this case. Now, concerning the second question, when we're dealing with more general convex problems, we essentially either, well, so far, all the problems we have worked with had a closed form solution for the proximity operator. But at one problem, I remember, I think it was the Poisson problem, image restoration. I think what we did is that we applied 10 PCG iterations to approximate the proximal operator in this case. Yeah, so I hope that answers the question.
Okay. Davide, is there any questions on YouTube?
No, we don't have any question on YouTube.
Okay. Okay. Thank you again for two speakers' great speech.
Thank you too.
Okay. Next session, Jemima and Davide, two of our committees, will give speech on May 10th. And thank you all for your attention. And we hope to see you later on Gather. Bye.